Okay. And this time I also have this visualization here because I realized last time I had the Galleria visualization, which is not, I think, optimal to really watch the videos. I hope that will still be useful. I will upload them on the course website after the visual. Let's go to this. This notebook here, which is actually an additional section to the one that we looked at last time. So this is the second collab notebook. Are there any questions?
About the?
No, you had out. So
No, about the internet.
ah,
It's about the internet.
okay, okay. No. So this is, as I was saying, it's an additional part on the second notebook that we had last time, which contains the solution to the exercises that we solved, or that were listed at the end. So the exercises were basically solving the unconstrained and constrained quadratic programs to basically solve the inverse kinematics problem for manipulators, for two types of manipulators. So if you recall, so exercise 1.
Yeah.
1 was basically yes. So we had a manipulator where n, the number of degrees of freedom, was less than or equal to r, the dimension of the task space. So in the specific exercise, n was equal to 2. We have 2 joints. And r, in this case, was equal to 3. Because we want to control the position and orientation of this part. Right, so we can specify an x, y, x and the vector, y and the vector, theta and the vector, as a point and an orientation that we want to achieve. But as we will see, we have 2 degrees of freedom to control 3 variables. So the unconstrained optimization problem to solve this problem was minimize q dot over q dot, the difference between j, q dot, and xe dot. Where this xe is equal to xe desired minus xe. This is the desired goals. Right, this is I think this is solved in the notes. Right? And this is for, I think I've updated also the notes to clarify that the solution q dot star of this optimization problem will drive the robot to a location, to a configuration that is as close as possible, right, to the desired pose of the element. This is what we call the x e bar, x e, and the p bar, right? So the desired configuration. So this is solved in exercise here 1. Let's see. Yeah, this is, so first of all, this class is the same that the one we used in the first column. Right, so there are the same classes, the R, the RRR with forward kinematics, differential kinematics. And in this case, I call it with inverse kinematics because that's literally what we are doing here. We are driving the robot to the solution of the inverse kinematics. And where we can set a desired force. Right, we can set the desired force here, which is this xe bar, ye bar, and theta e bar, which in this case are going to be minus 0.5, 1.25, and pi as an orientation. And then we will just execute the solution of this optimization problem, which is a QP. Right? So this code is exactly the same as the one that we saw for a generic unconstrained optimization program up here, if you recall. This one. Right? To figure out where the X is within the solve QP. Right? Without any constraints. So just the Q and P of the process. Which, by the way, these Q and P are not related to the QP. Yeah? So QP means quadratic program here. Q and P here are just the names given to the matrices and vectors that define the cost. So let's try to run this. So what happens is that at each iteration, we run this step function, which computes the inputs using this function, right? And then moves the robot as with the Q dot resulting from that optimization. So in this case, we are starting from, let's see, from this configuration, right? And we want to go to this point with this orientation. In this case, in particular, n is equal to r, right? Because we have 3 degrees of freedom. But this same formulation works when n is less than or equal to r. You can try it by removing one of the links and with the rr and see what happens. So in this case, you see we have the forward kinematics represented by this green dot and red arrow of the end. And then we also have what we saw in the differential kinematics. So this magenta line here is the velocity again, right? Resulting from the Q dot. So if we run this program, we have something like that that achieves these. Now you saw that there was quite a big jump, right, at some point. That was related to the fact that I think, as we briefly mentioned, we have the Jacobian J, which can be very close to the singular. Right? So this can be a problem in the optimization, but in the next actually, or in the bonus, what I call the bonus exercise, there is a way to solve this. Right? In practice, because this is really not a problem in practice. Can be solved easily. But I'm actually encourage you to try these different configurations, different poses. For example, here I have another one where just the angle, the desired angle, the effect of changes. So same position, but instead of pointing this way, we're pointing down. Right? Aha. So now this is something that is unreachable. Right? So it tries to reach this configuration, but it can't, right? Because the length of L1 and L2 is too short, right? To go to that position. So there is something that doesn't work, right? In this case. We'll see how to solve this. Yeah. For the exercise 2, instead, is kind of the dual of this. Because in this case, we have more degrees of freedom, and in this case 3, than dimension of the task space, which in this case is set to be 2. So R is 2, and why is that 2? Because we are only interested in moving this point to a desired position without orientation. So the task of the desired position is just xe bar, ye bar. some position, which is two-dimensional. So the task space is two-dimensional. Now we have more choices, right? To get this one. So that formulation does not make too much sense. Instead, the following constraint quadratic problem makes more sense. So among all the solution or all the velocities q dot that are satisfying this equality here, where xe is again xe bar minus xe. We want to pick the one that minimizes the square dot, right? Because we have a lot of them, infinitely many in some situations. Which one do we pick? The one that minimizes the square dot. So this is what this optimization problem says. And this is what it is solved in exercise 2. So here I called RRR with inverse kinematic redundant, because that's what robots that have, or for which n is greater than r are called. They are redundant because they have more degrees of freedom than the ones that are required. Let's keep it asking. And so you see the only, and this is all the same, the only thing that changes here is the solution of, or the formulation of the optimization program to compute the inputs. In this case, it's a equality constrained quadratic program. So here we have the Q matrix and the cost written in this way, Q dot transpose Q dot. Here there is an identity matrix. Here there is 0, right? So those are the quadratic and linear terms that we need to pass through this function, solve QP. Are given here. So the identity 3 by 3, the 0 vector 3 by 1. Then we have no inequality constraints, which would be passed as these two arguments. And we have this equality constraint. So we need to pass this and this third, right, to the function. And then we return the Q dot, which solves this Q. Then it's all the same. Yeah, but it's less redundant because it starts from random initial conditions. This one. There we go. So now you see that the desired pose here is just a green dot, right? There is no arrow or that indicates the direction. So R is 2. We are only interested in driving the end effect to that position without caring about the orientation. And the model of the robot is still the same. And this is what happens. So in this case, based on basically the initial conditions, right, we will get different final orientations. For example, let's try to rerun it and see what changes. Right, so in this case, it was in a different initial condition, it just goes there without caring about reorienting the end effect as it was. Cool. So now there is basically one last, I call it bonus exercise, because it's kind of mixing the two together, which also solves the problem of that infeasibility or impossibility of reaching a desired end effect. In fact, this one works for both cases. The case where n is less than r, and the case where n is greater than r. When you have less degrees of freedom or more degrees of freedom than the ones required to solve the task. So it's quite convenient, and also the cost shows that it's kind of a mix between the two, or the optimization problem shows that it's a combination of the two. Because now what we are asking, but this is to minimize over Q dot the difference between JQ dot XE dot squared plus some constant A kappa even greater than 0 times the norm of Q dot. So at the same time, we're saying try to match as closely as possible XE dot, the desired velocity of the entire vector. But at the same time, don't move too much. Right? These are the two objectives. There is no constraint, but it's just an unconstrained quadratic problem. And you can try to solve it by hand. Actually, this is quite simple, right? Because you just need to write down the necessary condition for optimality, which is the derivative gradient, right, of the cost is 0. And then since this is convex, that's going to be the global unit minimum, right? But here is a solution using the solve QP function, where you see it's unconstrained, but now the cost Q and P determined by Q and P is different. So we have J transpose J, which comes from this, which is the same as exercise 1. But we also have the identity matrix, which comes from this. Right? If you expand these norms as done for exercise 1, you will find that the Q, so the quadratic term looks like this. The linear term, which comes only from this term, right? This is purely quadratic, or yeah, this is purely quadratic. This has also some linear term. Is the same as exercise 1. So like that. And then solve QP, pressing in these matrices, and now we can do anything, right? So the first simulation is going to be giving a desired position and orientation of the entire vector that is achievable, right? And this is, I think, the same or similar to the one given in exercise 1. Right, there we go. It starts wherever, and then it goes to the desired position and orientation. And then aligns itself. If we give a desired pose that is not achievable, I think this is the this is the one considered above when we want to reach that position, but the orientation pointing downwards. This is whatever. And this position is optimal, right? You can see that kind of minimizes the distance in x and y and in the angle theta, right? And it does so by also considering how much velocity you need. And in the same way, you can also give just the desired position. So in this case, the manipulator is redundant with respect to the task. But the same formulation works in the same way, right? So in this case, we don't care about the orientation. And if you run this simulation from different initial conditions, it's gonna achieve different orientation than it doesn't control them. Right? I'll leave you experimenting with this actually and see what happens by changing different things, like for example the kappa here. Right? Which means how much we are interested in not moving, right? How lazy we are, right? With respect to how well we should match the x dot. You can imagine that if this kappa is super high, we are not gonna move. Because we are paying too much cost, right? To move. So we're saying, yeah, it's good enough. Right? I don't move. I'm close enough, right? Measured as this norm to the xe dot, right? Because I'm lazy. It's too costly. Yeah. All right. Yes.
They cover the some kind of function.
Oh, you mean depending on some parameters? Definitely. Which parameter were you thinking?
I was thinking about the PID method.
Yeah, to do what?
Change the position. Change kappa, like if you are too distant, you may move more faster.
Yeah, that's a good point.
If you are too close, but you are not achieving the desired position, go a little bit faster.
Yeah.
But
Yeah.
not much.
That's a very good point. Because if you look, you zoom in here, we're never gonna reach that point because at some point the cost, this one, right? Is gonna be I mean this one is gonna be much higher than this. So it's better not to move, like achieve something that is not exactly what we want, right? Because we will need to still move. And this is small enough, right? So we in a way settle, trade off at some point. And as you increase kappa, this trade off becomes more and more visible. And to the point that we don't move, we don't even move, right, at the beginning. So that's a great point. You can even tune it manually, right? You can even have an operator, a human operator, that interacts with this. Now robots will change these parameters. So you have what is known as exogenous, right? Like, where it doesn't depend on the state of the system, like the configuration of the robot or any other parameter, but it's completely coming from outside. More questions about this? The exercise. Okay, so if not, we can move to the topic of today's lecture, which is the so-called stability line classes for robots. This is the result. Which is going to be not our first controller, right? That we designed in this class, because the solutions of these exercises were already robot controllers, right? Remember, so we call it the feedback control system. Yeah, there are also the sensors. That looks like this. Here, but here is the system model. Which could be, as we said, x e dot equal to j q dot for manipulators, or q dot is g of q times u for mobile robots. This is what we will work with. And here is the controller. Right? And the controller gives as output a q dot for the manipulator or a u for the mobile robot. And this is exactly what we did, right? For the case of exercises 1, 2, and 3. We computed a q dot, specifically for manipulators, based on the state or the configuration of our system. So specifically, the picture for these exercises looks like this. So we have these are q dot star, and here we have an x e dot equal to j dot. So here as output we have an x e in a way. We have x e dot, but the integration step, right, inside in the stack function. So we get rid of where it is, and where Q is. In this case, we don't have any sensor. We just we just assume that we can directly access Q and X, right? So the sensor is perfect, which means no need of sensor block. The measured X, and Q are the same as the actual. So that's a parenthesis. Inside here, there is the controller, which is minimize over Q dot, blah, 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 subject to. And in here, we need Q and XC. Right? So, for example, here, XC is showing up here. Q is showing up here. Right, so these are the configurations, right? The stage in which the system is. Same thing here. Right? We have Q here and XC. So in a way, we have this feedback loop in here. The reference, which here we had as a state difference, right? Or we had entering a state like summation block to calculate the difference. Here is showing up as XT bar. Right? So what here was the reference. Here is XT bar. That is a parameter of the controller. But the structure is the same. So in a way, those solutions of these three exercises were already controllers that we designed for a manipulator in this case. So today we will see a general case where we will execute tasks for manipulator and mobile robots, which will consist in driving the state of the robotic system to a specific set of interest. Okay. This is what we call the stability-like tasks. Let's see one. All right, before we do that, since we're going to treat these two systems equivalently, manipulators and mobile robots, we will express them in a general form, actually for robotic system, which is the so-called control affine. Control affine. Which besides being very common in the robotic system, is also very useful for the optimization-based controllers, because it results in computationally treatable problem. And we will see why. So this is as follows. I think I've used this term, this symbols. X is used to denote the state. That is a vector in Rn. This vector. Right, is the state. We consider it to be a vector in Rn. U is the input, which is a vector in Rn. And then we have F0 and F1, which are two vectors. So F0 is a function that maps from Rn, that takes X in Rn, and gives as an output a vector in Rn. So F0 of X is a vector in Rn. F1 maps from Rn again, takes x is equal to Rn cross n, the matrix n by n matrix. Right, so f1 of x is a matrix which multiplied by q gives a vector in R. So all dimensions equal together. Now, first of all, let's check that these two are in a way expressible in this form. Right? So for the case of the manipulator, we can define the state x to be right x e, the end effector post, and the input u would be the joint velocities below. What is f0? Well, we need to somehow reproduce this. Even this two. How do we write that in this form? This is xe dot, this is q dot. Yeah, this is zero function. For any and for any x, this is equal to 0. There is no such a term. F1 instead is what we call K, but since we need to express it as a function of x, which is xe, this is composed with the f inverse. So this is the inverse kinematic. Function. Let's see whether it works much easier. So let's write this down using this formula, right? Or this definition. We have xe dot equal to 0, which is at 0, plus j composed f inverse of x times 0. This is equal to j and inverse of xc times 0. Right? And the inverse kinematic function gives for an xe the q equation times 0. So this is possible to be expressed in this control of line. Is that it?
That must have an inverse.
Yeah, so that's a great point. This of course only works if this q exists, right? So for a given xc, I can back up at least one q. Right? So again, restrict the function to have somehow a one unique value for q, but that unique value has to be right? So the xe has to be achievable by the law. So that's the example that we saw, for example, exercise 1. So the xe has to be achieved.
I mean, if we have two. Well, Well, that wouldn't be a function at all.
Yeah, exactly. So you need to restrict its domain to be able to just give you one value as f inverse of x. But that's in a way very easily you can handle it in a very easy way, right? Because usually if there are two configurations that achieve the same xe, so two q's that achieve the same xe, they are different from each other. They're very far away from each other in a way. So if you are close to one, then the robot cannot jump to the other, right? In practice. So in a way, there is a clear choice between which configuration q has to be the inverse of that, or the value of the inverse. Yeah. But that's a good point to keep in mind. Then the other one, the other case is the mobile global. These are much easier in a way to handle because it's almost one-to-one, right? We are reading here by defining our state to be the configuration of the mobile robot Q. The input is, U, what we call U as well for the mobile robot model. And this is without equal to G of Q times U. F0 again is equal to 0. So f0 of x is always 0 for all x. And 1 of f1 is equal to G. And with this in place, we have Q dot is our x dot equal to 0 plus G of Q times Q. So this is also easily expressible in this control of time. So two notes. Do you know why it's called control of time? Or can you imagine why it's called control of time?
Well, actually, because it's a function of mission.
Yeah. Space. In a finite function of the controlling U. That's why it's controlled of time. The second thing to note is that F0 here, we never saw a model with an F0, right? So far. So F0, in the case of robotic systems, which are derived or can be derived using analytical mechanics, so Euler-Lagrange equations, for example, this term contains the inertial effects. And in the kinematic models for manipulators or mobile robots, there are no inertial effects. What does that mean in practice? If no matter how fast I'm moving, for this Q dot, if Q is 0, I'll stop right away. So if I give as a controlling U 0, then Q dot is equal to 0. Right? Right? It's like you can imagine that this is not the case for an auto vehicle like a car, right? If you just raise the acceleration pedal or brake at the maximum braking force, right? You are not stopping immediately, right? You're decreasing the velocity, then reaching 0, and then you stop. That's the inertia, right? Because you have some velocity, which needs to be driven to 0 before you can stop. In this case, in a way, it's like the radio controlled, right? Vehicles, which in a way are very light, right? So the mass is very small, the inertial effects are in a way small, and the motors are extremely powerful compared to what they need to do. So if you just raise or remove the acceleration input, right, they will stop immediately. Right? So you can think of it. Or that's the case for a very slow car. Right? If you don't move too fast, then no matter, sure, the mass is 2 tons, right? But if you don't move too fast, the inertial effects are small. Right? Don't accelerate and decelerate too fast. Then if you brake as hard as you can, basically you're stopping right away. Right? So it's kind of this model. So, but in the two models we will consider, there is no inertia. Right? There's just this structure. In the notes, I also have the example for the dynamic model of a manipulator. The one that we didn't talk about in class, but it's in the lecture 1. So this is dynamic model of manipulator. And that's what can be written as this. If you recall this, I think I wrote down this at some point, but we didn't talk how to reach this point. But basically, this is the inertial capacity. So in this case, there is an F0 which is non-zero. The derivation, or not derivation, really is just rewriting it in this control of line called is notes. But here is because we are considering the dynamic. That's what it is. All right. So given this control of line board, now we will talk about this class of tasks that will be executed using robots that are modeled by this in this way. So tasks on the we will see 2 task models in this course. One today, one next time, in Wednesday, which are very useful to express a lot of robotic tasks. We'll see there are plenty of behaviors that you can achieve using these 2 models of tasks. The first one of which is the so-called stability type. Tasks. Which, as I said, consists in driving the state X of our system from wherever it starts at time t0, so its initial condition, to a desired set S. So as we move in space, we need to get closer and closer to this set. That is what it means. So this is the trajectory of our system X of t. And eventually we want that X of t reaches S. So it goes to S. I write it in this kind of informal way. S is a set X of t, the number. This is not a limit. Like this. You are seeing this symbol. So it's going to belong to us. For t that goes to t. This is this feature. So we start at x is 0, and then as time goes on, we are approaching the set S. We're getting closer and closer to set S. At some point, we are going to belong to the set. For example, as t goes to t. I don't know if you know anything about the stability of systems. I think you said you have some knowledge about stable points, unstable points. That's literally the same, but in this case, S is a set. Right? The stable points, asymptotically stable points, is x bar. X of t starts at t0 and then is going to x bar as time goes to t. That's the analogous for a generic case. Do you believe that this is actually useful for executing tasks, robotic tasks?
Yes, indeed.
Why?
Well, because your robot could never achieve the S space that is a real. And that's a problem.
No, but I mean, what tasks do you think we can execute, right?
Oh,
With this kind of task model. Let's take the example of the exercises before. Do you think that can be a stability like task?
Yeah.
Like going to a desired pose or the end effect. Right? So in that case, the set is a point, which is what we call the XE bar. Right? Let's get rid of this. I think I can also get rid of this guy. We'll remember it. Moment. Examples of these tasks. So one would be our manipulator that wants to reach a desired pose. So let's give a follow to this set S. Right? In this case, the X of the end effect of desired. So yeah, we should. The whole pose, by the way, is our set. So the manipulator that moves to reach this from its initial state is executing this kind of task. What if we just need, for example, an orientation to the end effector? We want the end effector to point upwards, for example. This is a theta E desired. Doesn't matter where it is, just want to point upward. Right? This is actually not a point, right? But now in space, it's a set. Right? It's the set of x's, xe, sorry, the end effector, such that the theta E is equal to theta E1. So it's like a plane, right? In the x, y, theta space. X E, Y E, theta E. This is theta E bar, right? The seconds is this way. It doesn't matter where X, E are. You just want to drive this. Yes.
So where can I use these non-trivial answers?
You mean like that?
Yeah.
Where can you?
Yeah, like if S is not a singular point, where can I use this?
Like in this case, this is an example of where S is not just a point.
Yeah, but like a real machine.
Oh, so okay, you mean a real machine? Yeah, a practical application. Yeah. So for example, if you have, imagine you have a camera here, right? Mounted on the end effector of your system. And you want to point it to some direction, but you're not interested in where exactly this end effector is. You can use something like that. You just want the orientation to be something specific. Or you have a light and you want to illuminate towards a certain direction. Right? But you're not interested in exactly matching the position. This would be an example. If you are interested, for example, in controlling a robot that helps a human to screw something, like a big piece, right? That needs to be screwed somewhere, right? And you want the manipulator to help you holding it in this specific orientation, and then you can move it on this plane. Then that can be very useful because the orientation is what matters, what allows you to screw, right? But then you go and you place it where you need, and then you can let it screw. Right? So there are plenty of examples where you might be interested in controlling just, for example, just one component of this task, and then all the rest are free, and that results in a set rather than a quantity. Yeah, that's good question. I think we will see, yeah, in the last lectures we will see examples of this kind of tasks. For example, this kind of camera that has to point somewhere, and other either similar tasks where S is not a trivial point, just trivial segment point. Other examples of this would be track the trajectory, right? So if you don't want to just reach a point, well, you can track the trajectory of, and that's an example for the mobile notebook. So we have our unicycle, for instance, and we want it to track this trajectory, right? So this will be a set that moves in space, right? So this S, oh, this was green, sorry. So the green is the desired trajectory. So at each time, we have that S is a point U. So as time goes by, we have that S at D1, S at D2, right? Moves on this trajectory. And so at each point, we want to go to this set. Right? So also trajectory tracking is a task that can be modeled in this way.
But it is a specific way in which to actually have not the time going to infinity, you have a specific time space.
Yes, yeah. So in this case, at time t1, we have just this point. Right? At time t2 greater than t1, we have this point. There's a set that moves. The example of the orienting a camera here, you have that you want different orientations. Right? So this data, right, this plane can move up and down as time advances. Right, you have a function of time with that. So a set that is function of time. You can restrict the x and y's. So this is like a plane that then becomes just a region, that shrinks to a region, or then becomes a whole plane, and so on. You can have all sorts of dynamics like that of your set designs. Now, how do we execute these tasks? And this is a model. How do we actually go to this set? Now the question is, in other words, right? We have our model for the system, the control of time, and 0 x plus 1. Now we need x to go to x. And how do we do that? By a control input u. So we need to pick a u. Pick u such that x goes to x. U, for example, is u is a vector in our n, so we need to pick m values to control x, which is a vector in our n, there are n values. We go to specific places. This is not an easy problem in general. Well, this is the essence of kind of control, right? You can solve this problem in all cases if we are done with control. Don't need to worry about that anymore. So there is a way to greatly simplify this problem. To basically a one-dimensional problem, which is the following. If we could find a function b, that maps from Rn to R, So we give a vector in Rn, specifically we will give x, and we will get v of x, a real value, such that when v is 0, so v is 0 if and only if x is 0, right? Then all we need to do is to drive d to 0, right? Which is one value. And if b goes to 0, then we are sure that x is 0. More formally, we will need b to be so-called positive vector function. So v of x is greater than or equal to 0 and of x. And v of x is equal to 0 if and only x is equal to 0. So this is positive vector function. Is something useful to reduce the problem from 10 dimensions to 1 dimension. The other thing that we will use is that v is continuously differentiable. So all derivatives, right? We can take the first derivative and it's continuous. So it's in a way you can imagine that we can figure out how it moves, right? By taking its derivative, its first derivative. Now, what do we do with this v? On this picture, actually, if this is the trajectory of x of t that goes from s, the analogous trajectory of v is something like that. So v starts at v of t0. Actually, I should write v of x of t0 to be precise. Right? So we plug in this vector x of t0, we get a value of v. And as x of t moves and gets close to s, v gets closer to 0. So this is the picture. Now you can see that seems much easier to do. We just need to control one value to 0. And then we are sure that this goes to the center. How do we do that? How do we make sure that that v goes to 0? As t is being given this sign. So here is an idea. What if we say, okay, v starts at some point v0, and then v dot is equal to minus v. This is first order scalar differential equation with the initial condition. Do you know the solution for this?
Alright. All of the use integrate. I don't have to use integrate. Smaller go.
Log or something else, like some inverse of log.
Oh, yeah.
Right? Yeah, it's exponential. I mean, all nice differential equations like that are basic exponentials. Not really, right? Because when you solve the differential equations, like in this case, linear, constant coefficients and everything, and you're gonna get an exponential. The basis functions that you use are exponentials. Cosines and sines are complex. Long story short, P of t is equal to V0 e to the minus t minus t. Right? And how does that look? This is the T0 starts here, well, at T0. Starts here, goes to 0 exponential. This is this function. So this is a good in a way to make sure that b goes to 0. Now, this might be too strict. Right? We want exactly b to follow this curve in its way to 0. It's stricter than we would like. I mean, there's no use in restricting b to this exact curve. What we can say is that as long as you are below this curve, you're always gonna go to 0, and you're free to move below this curve. So this is the solution of this a solution of this differential problem, which is like that. Which is like that. So b, instead of being equal to minus b, is less than or equal to minus b. And a solution of this problem is this red curve. Something that starts at the same place, but then is always below. And if it is always below, and it's positive definite, cannot go here, cannot go below 0, then it's gonna go to 0. Right? Right. Is that clear, or you have like doubts on this? Does it make sense?
I'm just thinking about the trajectory that you're picking. You see,
How we are picking the trajectory is the exciting thing. Using optimization. Now we're gonna end with that.
Oh, the minimum trajectory.
The one that, in a way, is optimal with respect to sum cost, which means we will see. I don't want it to be like which one is not optimal. But how we pick that trajectory is a very interesting point, very interesting question. So now, how do we make B move in this way, right? Following this dynamics in a way. We need to figure out what B dot is, how we can change the B dot. What is B dot? Right? B dot, which is d dt, right? Right? By chain rule, since B depends on x, right? We can write it as the gradient dv dx, so the derivative dx times x dot, so dx dt. Right? And dx dt is equal to the control of line that I just erased, right? So at 0 of x plus at 1 of x times u, which is the dx times at 0 of x plus the v dx times at 1 of x times u. So this is the dynamics. These are the dynamics of V. And look, they are control of time as well. Here is whatever, a function of x. Here is another function of x. And here is the u. So now we know that by picking a u, we can influence p dot. By the way, these dimensions should match. Right? So the VDX is a n, sorry, is a 1 by n vector. F0, as we said, is F0 of x is n by 1. The VDX is 1 by n. F1 of x is n by m, and u is n by 1. Right, so all dimensions match. When we get out in the scalar, which is CBUT. So now we're picking m number. We need to pick m numbers for just to control just one single value, which is p dot. And now we are almost ready to write down the which values. Can I this is? Yes. So we're almost ready to write down the optimization. We just need one more step because we want p dot, which now is equal to this. To be less than or equal than Vx, sorry, minus v of x. So what is this? It's a constraint on u. Constraint on u. In particular, this constraint is, well, a positive constraint. And is affine in U. And now you see why these control affine structures models are useful in optimization. Because now we get a affine constraint in U. We can easily fill a convex problem. Because this is a constraint. We use this as a constraint, right? And we carefully choose the cost, we're going to get that's optimization. All right, now we have the constraint. So as long as we pick u such that this holds, then b is going to go to 0, which means x is going to go to 0. So, sorry, x is going to go to s. So, pick u such that this holds. Then b is going to go to 0. That means x is going to go to s. And we're done. How do we pick u? Back to your question. By using optimization. So we'll pick the best u, right? Which is the solution. Which is the solution of the following optimization program, which reads like that. Minimize u, when you minimize over u, the norm square of u. Subject to dx f0 of x plus dx f1 of x u less than or equal to minus dx. Right, this gives us a u optimum. You start. what is the properties of this U star? So first of all, it is satisfying this constraint, which means x is going to go to s, and it minimizes the square norm of vector B, right? So in a way, this U star is called the mean, so minimum norm controller. Which minimizes this norm. And since this norm, so the norm of the control input U is somehow proportional to the energy or the power that we put in the robotic system, this U is a torque or is a velocity, right? This is also known as the minimum energy. So mean energy. Which, in other words, means that we are going to pick the smallest U, subject to the constraint that x goes to s, which means we're going to go to s in the, again, laziest possible way. We're going to spend the least amount of energy with us. Now, two notes. A function V, continuously differentiable positive definite, that satisfies this, that we can use, right, to build this constraint, is called a control Lyapunov function. Let me write it down. But there is a number of conditions to write in the right position. So in general, P R N R continues to be differentiable positive definite.
You were talking that V is like energy, so
Yeah.
it's like the total energy or just the potential energy?
That's a good question. It is the total energy. Yeah. I mean, for mechanical systems where you can talk about kinematic, kinetic potential energy, V can be defined as the sum of the two and work.
Okay.
Right, in this way. Yeah, so that's the analogous with the energetic of this thing. The energy is also energy both positive. But yeah, so V like that is a control Lyapunov function. Sometimes abbreviated CLF. For the system where x dot equal to fx plus gx times u. If in this case there exists a function, we call it alpha, which is of so-called class K. I tell you what this is. A very simple function, but it's called class K, such that for all x's different than 0, there exists a u such that that inequality equals. So dp dx at 0 plus dp dx at 1 times u less than or equal to minus b x. So there exists a u such that you can solve that. Okay? Sorry, minus alpha of the x. Yeah, to use this function alpha. You see, you already see in a way what this function is used for. Is used to in a way to control how fast this v dot goes to 0. We chose before alpha to be just the identity function, right? This was minus v of x. Alpha can be any function which is continuous, strictly increasing, and 0 at 0. So any function that goes like that. In general, you don't care about what happens for values less than 0 because these are positive definite functions. So these values are always greater than 0, greater or equal to 0. So you're only interested in this part, but that extended version. So the idea is that you can pick a rate at which v goes to 0, such that for all states x, you can pick a u that satisfies this inequality. So different types of alpha will lead to, for example, the following pictures for v. This is for an alpha 1, this is for an alpha 2, this is for an alpha 3 function. They just determine the rate at which they go to 0. One straightforward function that satisfies these properties, which is called a class K function. Class K is the linear function. Just alpha like that. So this is alpha of s equal to a times s, right? For a greater than 0. It's just a linear function with a positive coefficient, right? The positive inclination. So it's continuous, passes through 0, and strictly linear. But this is in a way a larger class, right? From where you could pick. For our purposes, we're going to use linear functions. They work, and they are they give us enough freedom to change these rates in a unique way. So in fact, this is node 2 and node 1, because node 1 I wanted to define this control level of function. Node 2 is that we can pick in a way the rate at which v goes to 0. Again, remember, that is the rate at which x goes to s. That's the same rate, huh? By picking this function. That's what we're gonna see also in the collab notebook. Like looking at this picture, alpha 1 is the middle one. With alpha 2, x is gonna reach s slower. With alpha 3, x is going to reach like s much faster. Because p drops to 0 much faster. So x approaches s much faster. I know this is, I mean, it's much more confusing than saying it like that, but it's not that, I mean, it's not that difficult, rather there is almost nothing more than what we just said. It's just this rate that we can in a way tune. Do you have any questions on this?
You were drawing this all this statistics, I was just remembering variational conflict. Because it's really closely related.
I mean, the only link that I can see with that is the fact that you can solve like variational problems using optimization.
Yes.
Yeah. With this, I don't know. I don't know what would be the. Let's see. No, I don't know actually. I mean, I don't know of these alpha 1, 2, and 3 in variational problem. Definitely, like since that's an optimal control problem, what is in control is known as an optimal control problem. There is some function that goes to 0 as you advance time, which is the value function, right? The optimal goes to goal, right? Which I mean, there's some similarities with this, yeah. But I would not say anything more than that. I don't know what other similarities. But yeah, that's an interesting observation. And we're very close to optimal control. Now, this is all. In fact, this mean norm controller is also the solution of an optimal control problem with a different cause, different constraint, obviously. If you're familiar with optimal control, that's the in a way similar or the link between the. Yeah. In fact, if you want the, I mean, I can give you some references where there is the link between mean norm controllers and the optimal controller. Yeah, that's very cool. Yeah. In fact, I used it actually very recently to link this kind of formulation to the tasks which are learned using the so-called reinforcement learning paradigm. Because reinforcement learning is an algorithm to solve optimal control problems. Period. I don't want to hear anything else. but that means that there is this notion of a value function that you can use like in this kind of optimization problems and get the optimal solution with respect to the optimal control. But yeah, we have to talk about more about this offline. But it's not yeah, we're not gonna say anything more in these lectures. Let's see, there's anything else on this before the example? No. Yeah, no. I think so. I think we're ready to do an example, which I hope we clarify for listeners. Okay, so the example we're going to solve is very simple. We want, so we have a system which is x dot equal to u. Control of fine, right? F0 is identically equal to 0, F1 is identically equal to the identity matrix. Right, and we want x. So the task is x that goes to, let's call it x flat, go to some point. I think in the notes I have x that goes to 0. Let's do this here. So in more general. So the set S in this case is the set of all x's. It's not even all the time like that. It's a singleton x flat. It's one point. What do we do to, to execute this task? Step one is to define the Lyapunov function, p of x. So this has to be positive definite, and we need it to drag it to 0 when x goes to this set S. So easy candidate would be this. Right? This is always positive for all x's. And it's 0 only when x is equal to x bar, which is when x is in the set S. This is a good candidate. Then the step 2 is to write down that constraint. That that the constraint that you has to satisfy. So the constraint reads like dv dx f0 of x plus dv dx f1 of x. That's u less than or equal to. Now we have the freedom to choose the rate, right? Which is v will go to 0. That is the rate at which x will go to x bar. Whatever. Let's put a constant a. Right? Times b. So here the class A function alpha that we chose is equal to the linear function, right? The example, linear function example I gave. So how do we write this constraint for this problem with this b? So f0 is equal to 0, so this term vanishes. Then the dx times f1. This is non-zero. What is dx?
Yes. It's 2x minus x bar.
Transpose times f1 of x, which is the identity. We can write it, but it doesn't matter. Times u less than or equal to minus a x minus x bar squared. So this is the constraint for our optimization. Now we will write the mean norm, the minimum energy controller as the solution of this quadratic program. Because it's quadratic, constraints are fine. So this is convex quadratic program. This is actually quite simple to solve by hand. Last time we didn't talk about inequality constraints, but I hope you have time to go over them in the notes. Over the weekend or on Friday. But there is basically a system of equations to be solved and find the optimal solution. So in this case, let's see if I have them written, but the procedure is still the same. We define the Lagrangian to be the cost plus lambda, the Lagrange multiplier, which in this case is a scalar because it is a scalar constraint, is one single value, right? A scalar value times plus lambda minus 2x minus x bar transpose u plus a. So this that has to be less than or equal to 0 is our constraint function. Yeah. That we use to build the Lagrange. Then the system of equations that we need to solve is the following: dl dq at u star lambda star has to be equal to 0. Then we need that 2x minus x bar transpose u star plus a x minus x bar squared has to be less than or equal to 0. That's the constraint. Then we need that lambda times this, the whole constraint again. Sorry, lambda star, so the optimum. Has to be equal to 0. And lambda star has to be non-negative. I hope I didn't forget anything. Yeah. Yep. We can write what this is. This is 2 u star transpose. And then we have another term here, which is plus lambda star. So 2 lambda star x minus x bar. So this is a system of equations in the unknowns u star, which is a vector, and lambda star, which is a scalar. Is actually not hard to solve. No. In this specific case, when we have only one constraint, because in general it's hard because you have these inequalities, right? But here, combined with these equalities, right? So there are basically multiple cases that can arise. But in this case, they are easily handled by hand. So, oh yeah. We will do. From here we solve for u star, which is minus lambda star x minus x bar. Right? Which we can put here, then get it 2 x minus x bar transpose times the u, which is minus lambda star x minus x bar plus a x minus x, and this has to be it has to be less than. We can actually let's plug it in. So it's the same thing but multiplied by lambda star. So we have a lambda star squared and a lambda star. This has to be equal to 0. So this is the norm of x minus x bar squared. So what we get here is did I miss a 2? No. No. Yeah. Minus 2 lambda star square plus a lambda star. Right? So this is always non-zero when x is not at the bottom. So for x different from at the bottom. Then we have lambda star can be either 0 or what is that? A by 2. A by 2. Right? So we can should be okay. I would have done, right? Because then we can plug in here this. Right? In here, we get U star equal to minus x minus x bar, which is a bar 2 x bar minus x. And hope that's didn't run mistake. So this is our control, as simple as this. These are optimum control, actually, right? So if we pick a u equal to this u star, which is a by 2 times the difference between x bar and x, x will go to x bar at least as fast as the exponential with an a, right? Because remember the picture in green looks like that. This is e to the minus a t. This is the b of t, which is somehow below that. And the picture in x is the picture in x is just in space. We cannot draw any temporal changes, but x goes to x bar as fast as this b of t versus. So by picking a, we can regulate how fast it goes to 0. Right? With an a greater than a1 greater than a. Okay, this was the just a simple case. That's why we solved it manually. But we really don't need to do that, especially when we need to execute multiple tasks at the same time. So we're gonna have multiple constraints. So this is gonna become a real mess in some situations. Not even impossible to get a closed form solution like that, right? But that's just to see that this is nothing impossible, right? It's just a complex quadratic problem. This is one constraint that can be solved manually, but we will solve always using computational methods. Do you have any questions on this? On this example? If not, we will go to the third Google Colab. Again, the notes are updated on the website, Kingpost website. And inside the notes, there is the link to this Colab. And yeah. All right, so here there are two examples of applying this kind of organization-based controllers for stability-like tasks. In the case of manipulators and mobile phones. So for the manipulators, I think we use the same exact models that we had in the first Google Colab. So the Revolut manipulator and the Unicycle for the mobile as a mobile phone example. And the tasks are going to be similar to what we saw before, but this time using this kind of general also. Initially, I think, I need to install these PP solvers. This is a new notebook. And then these are all the functions copied from the previous Colab. Okay. This is the formulation, right? So we want, in this case, the end effector of our manipulator to go to XE bar specific pose. The corresponding inequality constraint, which is V dot, that depends on both XE, the state, and Q dot, the input, has to be less than or equal to minus V. In this case, I don't know if I used any different. I used 10 minus 10 times that as a class A function outcome. But I encourage you to experiment with different types of outcome. This constraint has to be enforced to drive B of XE to 0, and so X to XE bar. So the inequality constraint will be treated like that, and that's what we implement inside the compute inputs event function of this class. The cost is just purely quadratic, right, in Q dot. So identity for the quadratic term, 0 for the linear term. The affine constraint, inequality constraint, is defined by this vector minus 2 x minus xe transpose times j, and by this scalar, which is minus, in this case, as I said, 10, I choose 10 as a constant, times the difference square, the norm. And everything else is the same. This is just plotting functions for different cases. So if we run this with, in this case, desired position, we're going to get this behavior. Right? That's very similar to what we saw with the equality constraints. Right? In this case, it's just that we are that started too close to the goal. Let's do that. That means just like by random addition. The difference is just in the way it moves, because now we have an inequality. So we have more freedom, right, to minimize this Q dot, because we have a whole half space, right, where we can pick this Q dot, and that's why we get this kind of strange behaviors, right? Because that's the one, the behavior that minimizes the energy spent. Because you see, at the beginning, we are just moving kind of the last join. The other two are not doing much. So in a way, their norm is minimized, so they're kind of doing the same. And then at the end, since this has to converge to the green point, we let it move in that direction. It's really has to. As I was saying, you can experiment, or actually we can do it now. If we have some time. What happens if we have 20 instead of 10? What do you think?
It'll be fast.
Yeah, it's going to converge faster, right? Already converged since numbers. Okay. Okay, maybe not too much faster, as we can see that we can actually appreciate it by looking at it, but let's video. Yeah, that was extremely fast. You see the velocity of the end effector is this big now. Also some oscillation. These are mainly artifacts of the simulation, right? Because the J, so all the parameters inside the optimization program are changing based on the configuration. We have a J that depends on Q, right? So if the integration step is not small enough, then you get this kind of instability. That's actually not just a simulation problem, because these robots, right? All robots work at the same times. They're not genius time, right? So you need to make sure that these parameters are, for example, this function, this multiplier here is not large. Otherwise, you will actually get instabilities under your system. Similar, so the last example, similar example for the mobile robots. Or do you have any questions on manipulator before I go to mobile? Okay, so the system is different. Now is a unicycle. The inputs are different, or the states are different, but the formulation is exactly the same. So here we go over the importing of the libraries from previous collabs. But the formulation is exactly the same as I was saying, right? So we pick a V. In this case, it's slightly more complicated for a reason, but actually you'll see that this is not that much complicated, and we are solving a problem which is absolutely not easy to drive one of these unicycles at a specific point. We're basically able to park, right, at the equal to some specific point. Not easy, as I was saying. The V looks like that. We want to go to a Q1 bar, Q2 bar, which are X and Y in the V. And this last term is used to steer, right, the robot to point towards the goal. Okay. Right, because these are, let me read it up. So if we have the unicycle like that, and we want to go to this point, which is X bar, Q1 bar, and this is Q1, Q2. Then we want to align this angle, which is theta, Q3, with this angle. Which is the arctan of arctangent of Q2 bar minus Q2, Q1 bar minus Q1. Okay. So this is just to steer this, to align these two directions. And this is natural, but it's not easy, right? In general, to design controller to steer. That comes from the fact that these robots have so-called non-holonomical states. So the unicycle is not able to slide sideways. Otherwise, it will be triggered, right, to move a point right on the main. In this case, you need to steer and then go. Right? And this is just done by defining this function, like two quadratics sum to each other. So extremely easy. I mean, when you take the derivatives of arctan, you get a mess, but it's not too bad, let's say. And this is implemented by this optimization program here. Again, cost is the same. The P is, as I said, yeah, it is mess, but you can easily go once. And last term is minus, in this case again, minus 10 times the Lyapunov. Let's see how it goes. So here we again set the desired position, minus 2, minus 3. And we have the robot driving there. You see how interesting, right? The steering plus driving are combined together. We're not saying anywhere, right? That in the program. And the way they are combined, so how much we steer versus how much we drive, is given by this parameter kappa here that is used to combine the two terms of the control Lyapunov function. In this case, it's 10, and we will see what happens if we put 5. Putting 5 means that we are not too much interested, or we are less interested in steering towards the goal as much as we are in going towards the goal, right? So in moving. And now the steering should be somehow, you see, is much more pronounced in a way. Right? You can clearly see the maneuver, right? You can try plotting the trajectory if you want to see that have a clearer view of this. You can reduce it even further to see the effect. In this case, it started steering very slowly. Right? Towards the point. Right. Whereas if you increase K, what is going to happen is that the robot is going to steer towards the goal almost immediately or very fast, and then go straight. And these different behaviors are just one parameter. I'm almost turning in place and then go straight. Right. Questions about this? The last thing I want to mention is why are they called control Lyapunov functions? So Lyapunov is with a capital L, in fact, he was a Russian mathematician. I guess, yeah, at that point they were all mathematicians. There was nothing applied to control theory yet. Right? Maybe he was the first one to try to. Maybe him and Lagrange or Maxwell were the first one to try to think how this mathematics applied to control theory. But he was a Russian mathematician who developed this kind of theories that are useful in stability in general, in nonlinear systems. Okay, the most general class in a way of systems that we deal with. And the Lyapunov functions are functions that are used to, in a way, check the stability of a system, which means the stability of equilibrium points in general, which means if x is going to go to x bar, right, you can check it using a Lyapunov function. A control Lyapunov function is a function that is useful to pick a control input for that to happen, and that's what we did. Right? So that is the etymology of the word. Tomorrow, the next lecture on Wednesday, we are going to look at somehow the dual of this problem. Now we saw how to go towards a set of interest to solve a task. Next time we're going to look at how to stay within a set, which are going to be like invariance like classes. We want the system to be or a set to be invariant. The state can go wherever, but never has to exit that set. And with that, we can, for example, ensure safety constraints, very obviously in a way useful in practice. Don't collide with obstacles, don't collide with other robots, don't hurt the human, and so on. And then in the last two classes, we will see how to, or actually last one or two classes, we will see how to combine this stability and invariance like tasks in a single combination. Very last note is that I said one or two classes because probably the Friday class is going to be somehow like replaced by a meta class this week. I don't know if you had any news, but I'm also waiting for it. I'm not sure. As of now, I updated the schedule to basically get rid of the last Friday's class. In case it gets scheduled, we will have another one sometime this week. Right. So as again, if you have any questions, please send me an email with Wednesday if you have any questions before Wednesday. And if not, I'll see you I think on Wednesday. Then. Right? Right, ciao.